Welcome to Zaic Design's Pump Technology Guide. In this video, we'll explore various types of pumps and share insights on selecting and optimizing the right pump.
Every pump of this type has what they call a BEP, best efficiency point. I spent 10 years looking for this pump. The high flow through the pump may actually cause the pump to overload. Restricting the pump so less water flows through it reduces the load. Centrifugal pumps are the same way. If you completely close the valve and deadhead the pump, it will draw the least amount of power. With positive displacement, if you run the pump at half speed, you get half the flow. Side channel pumps, they obey a square law. When you change the speed of the pump by 10 times, you also change the flow rate by 100 times.
Let's start with a quick look at the different types of pumps.
There are two basic types of pumps. In the one type of pump, the positive displacement, the speed of the pump directly affects the flow through the pump. So if you run the pump at half speed, you get half the flow. The other types of pumps are all using some kind of other force like centrifugal force to produce the flow, or blades that produce the flow. And so they are not positive displacement. In other words, depending on how much pressure they're trying to push against, the flow will vary with the pressure as well as the speed of the pump.
Next, let's explore positive displacement pumps.
I'll show you a pump called a peristaltic pump. This is positive displacement, and the pump has a tube that simply goes in a U shape, and there's some rollers that simply squeeze the tube against the outer housing, and then they roll around, and that cavity inside the tube carries the liquid from one end to the other. Peristaltic pumps can do a fair amount of pressure. They are positive displacement. The speed you run at affects the flow rate, and they are also reversible. You can run them in reverse and pump in the other direction. And there are only a few pumps that are actually reversible. Peristaltic is one of them. So this is a pretty typical peristaltic, and they come in a huge range of sizes. This one here is also a peristaltic, works the exact same way, uses a flexible rubber tube, but as you can see, it's very tiny. And it's also variable speed, and it also can pump in both directions. Then we have this little guy. This is a diaphragm pump. In this pump, there's a wobbling piston that pushes on a diaphragm and causes there's a set of check valves, and it causes the flow liquid to move through it. Now, this is positive displacement. The speed of the pump directly affects the flow rate. However, this one isn't reversible because it depends on valves within the cavity to go in a different direction. And so the only way you can reverse this one is with external valves. Changing the direction of the motor has no effect. Okay. Then we have this guy, and this is a positive displacement pump, but this is a solenoid pump. There's a piston inside that vibrates back and forth in time with the AC frequency of the line. So 60 times a second, the piston goes back and forth, and there's a check valve on one end and a check valve on the other end, and it is a positive displacement pump as well. However, again, it is not reversible because it depends on check valves. Okay? So then we have, one more positive displacement. This one is an air pump. This is double diaphragm. There's a valve section, and the air goes back and forth and pushes it. And there's 4 ball checks because this is double diaphragm. And the flow comes in the bottom and goes out the top through these ball checks. Same thing, it's positive displacement, but it's not reversible. It can only go in one direction. Okay? So then we have some other positive displacement pumps. This one is called a progressive cavity pump. And it's kind of strange how it works. There's a stainless rotor, which is like a spiral screw inside of a rubber stator, and the screw kind of walks around in the rubber stator, and that walking action creates cavities that move through the pump. Now, in order to drive it, because it wobbles, you can see there's a drive shaft here with the universal joints on both ends, because the actual rotor just kind of wobbles around. Advantage to this pump is it can handle solids, and it can generate very high pressures, and the pressures are based on how long the rotor is. You can put a longer rotor on it, and you can pump as much as 3,000 psi in some cases. These are used to feed things like thick paste. They work really good with high viscosity stuff. They will pump food pastes and things like that, and so that's a real popular type of pump. They also use them in sewage plants to pump sludge. You'll see these out in the wastewater industry quite a lot. This is another positive displacement pump. This is a diaphragm pump that's electrically powered. It's kind of like this, single diaphragm, check valves both ends, and this is also, you can vary the speed of it, and it's a single diaphragm. So this has a lot of pulsation. Essentially, you get a pulse, then you get nothing as it's retracting, and then you get another pulse. Whereas with this one, the double diaphragm, the flow is more or less continuous. So this one is typically used as what they'll call it a sucker pump, because they can lift water quite a bit. They're self-priming, meaning that you don't have to put water in them to start them. They'll start from dry. And they're used to like dewater pits and things like that. And we've used them in waste treatment for bringing in raw sewage. It's another positive displacement pump. This is pretty typical pump used on high pressure washers. And this is a piston pump. Okay, piston pumps are used for very high pressures, low flow but high pressure. And these things are also can be produce pressures high enough to be used in a water jet cutting machine, where they use pressures over 60,000 psi. The downside to piston pumps is they can't tolerate any abrasives. Right? Now, it's a piston pump. The definition of a piston pump is that the seals are on the piston, same as in your car, where your car has piston rings. So a piston pump has the seals on the piston. And this is a plunger pump. And you say, well, what's the difference? Well, plunger pump, there's no seals on the piston. The piston or the plunger is just a straight cylinder. And instead, the seals are on the housing. And that's the difference. Mechanically, they are identical. They both use a crankshaft to push the pistons back and forth, but a plunger pump has the seal on the outside. Now, the benefit to the seal on the outside versus on the pistons is that quite a lot of these pumps are made with adjustable seals. So as the seals wear, they can be adjusted even while the pump is running and from the outside of the pump. Whereas a piston pump, in order to do anything with the seals, you have to disassemble the pump. So that's the general benefit of a plunger pump as opposed to a piston pump. But as you can see, they're very similar. They're both positive displacement. They both involve valves, so neither one of them is reversible. Then we have a lobe pump. Okay, so lobe pump has two rotors with a seal at the ends. These white areas, that's a seal to help reduce the leakage from between the rotor and the housing. And these are positive displacement and reversible. And the flow, as you can see, goes around the outside, not through the middle, which you kind of would think it would. It actually flows around the outside. So lobe pumps are used for pumping sewage and things that are thick, high viscosity and so forth. The downside to them is that you see the lobes. The lobes are not really gears. They don't drive one another. So actually behind this these rotors outside the casing, there's a set of timing gears that keep the two rotors timed. They're not self-timing. So they are, however, self-priming. They will pull liquid up, they will pump air and pull until they get liquid. So these are quite common in the wastewater industry. They're also being used in pumping permeate from membrane systems because of the fact that they are reversible. The thing I don't like about them is that they are reversible, but they also can generate very high pressures. So in a membrane system, when they're being used for a backwash, there's a real high risk of damaging your membranes if you accidentally have something closed. And I was actually at a plant where they broke a bunch of valves when a valve didn't open and the pump turned on and it just blew everything apart. Then we have vane pumps. Vane pumps are another type of pump where the rotor is not centered in the housing, it's eccentric, and it has these vanes that act as seals, and as the pump turns, the vanes are spring loaded against the housing, they go in and out, and in doing that, the cavity expands as it goes around, and so that produces the flow. Like the other pumps with no valves, they are reversible. They can pump in both directions. Normally, they do not. Normally, they do not because the vanes in most of these pumps are actually tilted and not shown straight as you see here, and so they don't like to be reversed. They don't work as well. They will, but they're not really intended to. Then we have gear pumps, okay? This typical straight gear pump like this, same as the load pump, works the same way, except that the fluid is in the teeth of the gear, and it flows around the outside from one side to the other, and that type of gear pump is often used in hydraulics to produce high pressures. It also can be used as a motor. This type of gear pump can be driven as a motor. There's another type of gear pump called a jar rotor pump, and this internal rotor kind of wobbles around. These are very popular as hydraulic pumps as well, and they are this is also used to make a hydraulic motor. So you'll have a motor that's being pushed by what looks like a pump that's made the same way. In the old days, I know of this as a Viking pump, which is an internal gear inside of an external gear. And same thing, positive displacement. And all three of these can run in either direction and are positive displacement. So that you can control the flow. And that's important for hydraulic motors and so forth. I guess pump, yeah, one more. So this pump, I could only find an exploded view, but this pump is a roller pump. This is kind of a hybrid. It depends on centrifugal force to keep the rollers against the outer housing. And like the vane pump, the rotor is not centered in the housing. And what it does is it creates cavities that expand and contract as they go around. But the roller is simply driven by the rotor. And the roller, if you think about it, it's being pushed by a stationary surface and then rolling against the outer housing. So the rollers tend to wear out quite fast. However, they're very tolerant to junk. And this is a really popular pump for farmers for spraying their crops with chemicals and stuff. They can get 300 PSI out of a pump like this, and the rebuild is nothing more than taking out those plastic rollers and replacing them with some new rollers. So because it depends on, it's positive displacement as long as it's running fast enough. If it's not running very fast, the flow can fall way off because it doesn't seal well. So, but it's a real popular pump and for that purpose. Last one. This is, again, kind of semi-positive displacement. This is a rubber impeller pump. Same story. You have a rotor which is off-center in the housing. and it creates a cavity by flexible rubber fingers against the outer housing, and the size of the cavity changes, and that's how it generates the pressure. This pump is really popular in marine. Uh, all your outboards and marine marine outboards use this as the coolant pump, and it's also fairly popular. You'll see them as a little pump you can buy that you can hook up to a drill, and they again will pump in both directions. You can see how the ribs are kind of deflected in one direction, but if you run it the other way, the ribs will flip around and it will pump in the other direction. So they're commonly used to like fill a bucket with out of a tank or something like that, and then you can reverse it and pump it back the other way.
Now we'll move on to non-positive displacement pumps and their flexibility.
The most typical one is a centrifugal pump. And the centrifugal pump uses a rotor. It doesn't touch the housing and spins in one direction, and the water or liquids get pumped by the action of centrifugal force, throwing the liquid out towards the outer housing, and then they kind of peel it off as it comes around. And these come in sizes from like this little guy and this one, which is also a centrifugal pump, to gigantic pumps that rated tens of thousands of horsepower. Okay. So centrifugal pumps are popular because they're very, very flexible. And that flexibility also brings some downsides, which I'll go into a little bit. This pump here is a submersible. It's also a centrifugal pump. The pump's at the bottom, the motor's inside. The whole thing goes in the water, and it's common used to pump out of tanks. Or, this is your sump pump that goes in your basement for when you get flooded. All right. And submersible pumps are very, very popular and made in all sizes. Gigantic pumps. You can get them with 20-inch discharge. They're just a huge range of pumps. The advantages of putting them down in the water, is that if they leak, it doesn't go anywhere. You don't have an issue with leaks. They also stay cool because they're in the water, and they're a good place since they don't have to do any lifting. They're in the water. You have positive suction head on the pump, and they're pushing water, and so you can pretty much lift the water any distance you want. This pump, this is semi-centrifugal. I spent 10 years looking for this pump. I say, why? Well, I didn't know it existed. Or I had heard it, but I didn't know how it worked. So this pump is called a side channel pump. And a side channel pump, the water isn't directly pumped by the rotor. The rotor is not, it's not a centrifugal pump in that it has a rotor that's kind of spiral. This has a rotor with straight blades. And the water is pumped in a channel on the side that is not actually the rotor. So you notice that it has the intake and discharge both on top. And the reason for that is this pump's self-priming, but only if you've put some water in it first. And as long as there's some water in it, it will pull air through, and it will pump and split the air and water out, and eventually you'll get the liquid to come up into the pump. And this can pull water from some 15 feet deep out of a tank. So the unique thing about it is that it's not positive displacement, doesn't have any valves, and it's reversible. You notice the arrow on the end. And this is how I found out about this pump, this type of pump. My boss had somebody send him a letter, an email, and saying, hey, I'm working for a pump company, and he sent a picture of the pumps they make. And when I saw the picture, the thing that jumped out at me was that arrow. And I realized that was the pump I'd been looking for more than 10 years to pump permeate from membrane systems. Because this pump, I can pump water, pulling membranes, but pull a suction from 15 feet down I can pull permeate off of the membrane, and then every so often simply reverse the pump and backwash the membranes. And there are no valves involved. Now, unlike the lobe pump that I showed you earlier, this one, there's no danger of blowing anything up because the pump is not positive displacement. It's limited in how much pressure it can generate. And the pressure it can generate is also a function of how fast you're running it. So that means that you've got lots of safety built in. You don't need relief valves and all this other complications for it. So it's a wonderful, wonderful pump for that application. This little guy here, this is a centrifugal pump, and what I didn't mention is this one's both centrifugal and it also has a brushless DC motor driving it, which is variable speed. And this pump is also submersible. This is an automotive pump. This can be put in a tank underwater and used as a submersible pump, or it can be external with hoses attached and run that way. And again, because it's variable speed, it's got a very wide range of flows. Centrifugal pumps are the most widely used pumps because they're very, very, very flexible. And so this is just a chart showing one pump company's range of pumps, all of one particular design. And these areas that are showed are for different pump housings combined with different pump rotors. So a centrifugal pump, they aren't just built one way. They're built as you select the housing, and the housing typically gives you choices on like what kind of ports they have, whether they're flanged or threaded or hose ports and so forth. And then you combine it with a rotor that goes inside, and by changing the size of the rotor, you change the characteristics of the pump. It also means that you can even tune the pump to a specific use by trimming the rotor. You buy a rotor that's a little bigger than you want, and then you trim the rotor to give you either better efficiency or a closer match to the flow with a fixed speed motor. This is a pretty typical looking pump curve. This is one size pump, 1.25 inches by 1 inch discharge. And as you can see here, there's 5 lines. Starts at 4.25, 4.75, 5.25. So these are all the size rotors that you could put in that pump. And each rotor then has its own curve. Okay? And when you talk about centrifugal pumps, you talk about them operating on the curve. And somebody will say, it's operating off its curve. They can't. They are always on the curve. They're just not on the curve where you want them. In other words, for any given flow rate and any given pressure, the line shows you what you're going to get at 1,750 RPM for this pump. Okay, now this pump will pump, with the biggest rotor, will pump like 50 feet of head, which is about 25 psi. Yeah, a little less than 25 psi, and it can pump all the way out to 80 gallons per minute. Right now, the pump will always be operating with that rotor on that curve. If you look at the pressure and you look at the flow, you'll find the pressure, and vice versa. Now you notice there's some curves here. Well, every pump of this type has what they call a BEP, best efficiency point. And the BEP is right here in this pump. And this pump at its best efficiency is 68%. So 68% of the energy going in produces flow. And you can see the curves. Well, if you operate the pump back here, right, if you're getting only 20 gallons a minute at 50 feet of head, the efficiency can be as low as 40%. Okay? Going in the other direction, it also falls off. So when you're trying to buy a pump of this type, you want to try to hit the highest efficiency for that pump. So how do you do that? Well, sizing the impeller is one way, right? If you choose a different impeller so that the flow and pressure that you want are on that curve, you get a better efficiency. Now, the other side of this is, as I said, the pump follows the inverse pressure laws. So here's the same pump, right? But this time at 3,500 RPM instead of 1,750. And now that same pump, same impeller, goes to 200 feet ahead and goes out to 160 gallons per minute. Right? So same pump, same impeller, speed makes a big difference. So that means if you put a VFD on a pump, you can. What does a VFD do to a pump? Well, essentially what it does is it moves the curves up and down. This curve is up at 200 feet. And this curve is at 50 feet. But those other curves are just above this. So this changing the speed essentially moves the curves up and down on the chart. Now, there's a couple of other lines that are real important. You see these lines here, the dotted lines or dashed lines. Those are the horsepower curves. So if you pick this impeller, the horsepower curve is above it, and so the entire range of that curve is usable because it falls under the horsepower curve for 0.3 of a horsepower. Now, if I pick the next impeller up, you can see how it crosses above the horsepower curve, which means that 0.3 horsepower motor is not adequate. I have to jump up to a 0.5 horsepower motor. So you always have to operate below the motor curve as well, right? And that's how you size the motor. So this same pump could be sold with 1/3 of a horsepower motor, or it could be sold with a 1.5 horsepower motor, which would then allow you to operate the biggest impeller over the whole range. So in my job at doing wastewater, a big part of my job was selecting pumps, selecting the impeller size, calculating what flows I needed, what pressures I needed, and then you go to the pump curves and you find the pump that will work for you. Now, this is for one size of pump. When you change the size of the pump, of course, you can get hugely different flows and capacities. But all of the centrifugal pumps, you'll always find a curve chart like this. And this tells you how the pump's going to work. So when you go out, like a customer's having trouble with the pump, and they say, oh, it's not working, and you go and you look and you say, well, what's the problem? Well, I'm not getting enough flow. Well, how much flow are you getting? So you pull out the pump curve and you look and you say, oh, well, yeah, okay, you can see you're not going to get the pressure you want with that pump curve. So the fix might be a different impeller, and then that may push you into a different horsepower, and so now you got to change both the impeller and the motor. And this does happen. It can be tricky. So there's another issue that you always have to consider, and that is, since you have this curve, and submersibles like this also have the exact same type of curve, if this is in a tank, and the tank's 10 feet deep, well, when the tank is empty, before any water comes out, it's got to pump up 10 feet, right? So when you're just picking this pump, you're saying, well, I need 20 gallons a minute from the bottom of a 10-foot tank. And I have to lift 5 more feet above that. So I need 15 feet ahead at 20 gallons a minute. So you go and you pick a pump that will produce that. Well, here's the problem. What happens when the tank is full? Well, now I have a pump that can pump 15 feet ahead, but I only need to pump 5. So what happens to the flow? It's huge. huge because of the curve. You see this pump, this curve is very flat. So, I get from 10 gallons a minute to 60 gallons a minute with very little change in the head pressure. So what that means is that two things can happen. One is that the high flow through the pump, because it's like that, may actually cause the pump to overload because it's now pumping a whole lot more water and will be above, by you taking the pressure off, it can be above the horsepower curve. And so you're going to have trouble with the motor, with it pumping properly. The other issue is that you can have trouble with the equipment that you're pumping to having a problem with the high flow rates. In sewage plants, it's typical to have a wet well with the pump in it, deep tank, pump at the bottom because it's coming in from gravity sewer, and then they pump it up into some kind of screening equipment. Well, we've seen the situation where the plant was designed for 200 gallons a minute processing speed, and so they have a screen that's capable of handling 200 gallons a minute, and they have a pump that can handle 200 gallons a minute in the bottom of this 10-foot or 20-foot deep pit. And of course, when the pit's full, the pump can pump 1,000 gallons a minute, and the screen gets totally overwhelmed. I've seen parts of a plant where they have it roped off, because if you walk there, you're liable to get a bath in sewer water, because if the tank happens to be full when the pump comes on, it's going to be bad news. So this is a toughie. You would be amazed at how tough a time we've had explaining this to civil engineers when they're telling us what they want for a pump and what they want for a tank, that you're going to overwhelm the equipment downstream. And the problem with handling sewer water is it has solids in it. So you just can't put a valve and you can push the pump back to the proper place on its curve by using a valve. And that's actually commonly done. Going back to the early days of my career, I hooked up a centrifugal pump on a cooling tower. Well, on a cooling tower, the water was going out and looping back to the pump. It was just circulating through the cooling tower. And the pump tripped its overloads because it was drawing too much power. And the guy that owned the plant says, "Oh, well, throttle the valve." I was like, "What?" It's like, "Yeah, close the valve on the discharge." I was like, "Huh." So I did as he said. We're meter on the pump, and sure enough, the current went down and the pump ran just fine. Well, definition of work, you have to be moving something. So restricting the pump so less water flows through it reduces the load. And to illustrate this even further, everybody owns a vacuum cleaner. What happens when you put your hand over the end of the vacuum hose or on the suction side? You hear the pump screaming, the blower screaming. Is that because it slowed down or because it speeded up? The reality is it's because it's speeded up. It is now running faster because when it isn't pumping air, there's less load. And the type of motor used in a vacuum is not speed restrained by the electrically. It's speed restrained by the forces acting on it. And so it will go a hell of a lot faster when you stop air from moving through. Right? And centrifugal pumps are the same way. If you completely close the valve and deadhead the pump, it will draw the least amount of power. And then as you open the valve, the power requirements go up. So centrifugals are really, really popular in the world because of all this flexibility, but at the same time, they have their issues with controlling the flows, so forth. That's one of the reasons that I've done things sometimes with positive displacement pumps simply due to the fact that I absolutely needed to control the flow rate or the pressure, and it was really difficult to do with this centrifugal pump. Although if you combine it with a VFD, you can get a very broad range of action.
Let's explore some ways to improve the efficiency and longevity of our pumps.
All the pumps that are not positive displacement their output, their flow through the pump, is controlled by the speed of the pump. And but it's not the same as the speed control with positive displacement. With positive displacement, if you run the pump at half speed, you get half the flow. With centrifugal pumps and side channel pumps, they obey a square law. If you cut the speed of the pump in half, the flow drops by 4 times. If you are using it for pressure purposes, if you cut the speed in half, the pressure also drops by 4 times. So there's a good consequence to this, because today we use VFDs. This is a variable frequency controller that will run this pump. And because we have a good way to control the speed of the pump, we can change the flows or the pressures very easily to match what we're trying to do. Now, most motors that are what we call an induction motor, they don't work very well below down to less than 10%. So the speed range, that is a 10 to 1 that you can effectively get with a VFD. However, when you change the speed of the pump by 10 times, you also change the flow rate by 100 times. So you can get a huge range of flow out of the pump simply by varying the speed. Centrifugal pumps also have slip. In other words, the water isn't always positively propelled by the impeller, but you can compensate for that. If you want to hold a certain amount of pressure, you may actually be having a very small flow, but you're running the pump much faster, so you get the pressure. So the combination of VFDs and other variable type drives give you a very wide range of flows and pressures out of a single pump. So that's the basics of pumps. I've only talked about pumps that I actually have experience with, and there are just so many more, it's not funny.
Thank you for watching Zaic Design's Guide to Pumps. For more videos like this, please like and subscribe. And for an in-depth article that complements this video, visit zaicdesign.com/blog.